In this module, I want to start taking a look at the fundamentals of SQL queries, because if you're going to learn how to exploit SQL injection risks, you need to start developing a really strong capability around SQL as a query language. We're going to have a look at some of the basics in this module, and then as the course progresses, we'll get into more and more complex queries and commands within SQL Server. Now, as I said in the introduction, a SQL injection attack can be mounted against all sorts of different relational database management systems. I'm going to focus on Microsoft SQL Server, but I'm also going to point out where you need to be conscious of differences in the language semantics between SQL Server and other relational database management systems. So with that said, let's go and take a look at the overview of this module. So we're going to cover a number of different things in this module. And firstly, as I've said a couple of times now, the success of a SQL injection attack is really going to depend on understanding SQL. In the introduction of this module, I mentioned that SQL injection attacks are often automated. And certainly in those cases, you can just point a tool at a web server and let it go and do the work for you. But this course is about actually understanding SQL injection, knowing what's going on under the covers of these tools, and being able to mount an attack manually yourself. There's only so far you can go with automated tools, and particularly if you want to exploit the more advanced concepts within SQL injection, you're going to need to have a pretty good understanding of that SQL syntax. So at least a very fundamental knowledge of SQL is going to be very important. I'm also going to talk about basic database behaviors. So how does a SQL server actually behave? What can you do with a SQL server, at least beyond just creating and querying tables? And one thing you'll see as the course progresses is that you can actually get right down to the operating system level with the SQL injection attack. You can start running commands on the host if the web application and database server are insecure enough that they allow the attacker to do just about anything. And unfortunately, that is often the case as well. So that's all I want to talk about in the overview. And what I want to do now is go and jump into SQL Server Management Studio and start looking at some SQL syntax. Let's jump over there now. One of the best ways to illustrate just how important SQL injection is to refer to OWASP, the Open Web Application Security Project. And OWASP creates an excellent document which is the 10 most critical web application security risks. Now I've got a number of different courses about understanding the top 10 in detail, either in a technology agnostic way, via a course such as Web Security in the OWASP Top 10, the big picture, or specifically for ASP.NET in my OWASP Top 10 Web Application Security Risks for .NET. So depending on your interest and level of detail you want to go into, if you're interested in OWASP, go and check out those courses. The reason that I want to show it here is because of where SQL injection fits into that top 10. So I'm going to jump down a few pages in this top 10 web application security risks document all the way down to the list of those top 10. And injection is right up the top. It's number one. It's been there for years and years and years, and it continues to sit here right up the top of the list of risks. Now, one thing you'll notice here as well is it's not called SQL injection in OWASP document. It's just called injection. And in fact, you can see a reference here in the description to other injection attacks. So OS injection, LDAP injection. There are different ways of mounting an injection attack depending on the target system. Now in this course, we're only going to talk about SQL injection. I may sometimes speak a little bit colloquially and say injection, but it's always going to be about exploiting injection risks in relational database management servers using SQL syntax. So specifically, to SQL injection, let's go and have a look at why this is still such a big deal. Why does it matter? Why do we still care so much about this risk that's been around for so long? I want to break this down into 4 different categories. And the first one is discoverability. And the thing about injection risks is that they are really, really easy to find. You can easily find injection risks very often by just typing a single character in a URL. You can also very easily find SQL injection risks just via a Google search. That's all it takes. Carefully craft a query to look for a typical vulnerable URL, and it doesn't take very long at all to find lots of sites at risk of injection. So discoverability, easy. Prevalence is the next problem, and it is very, very common. And that goes to the point of just how easy it is to find via a Google search as well. The other thing that supports that prevalence is just how many headlines you see of systems that are being compromised by exploiting a SQL injection risk. And we'll see some of those headlines at the end of this module as well. So SQL injection is everywhere. The next problem is around exploitability. And the problem here is that it's just so easy to exploit a SQL injection risk. Now the risk itself can actually be a bit complex. The thing that makes it easy is that there are a lot of easily automatable tools out there. And we're going to look at some of those later on in this course as well. But a SQL injection attack can be as simple as copying a URL, pasting it into a nice little GUI attack tool, and then suddenly you've exploited the system. It can be that easy. It is so easy, I've got a video on my blog of my 3-year-old exploiting it, just to illustrate the point of how simple it is to exploit a SQL injection risk. Now the final problem, and this is the real sting in the tail of SQL injection, is the impact, and it is severe. So when we talk about impact of an injection attack, we're talking about the potential compromise of all the internal data of a system. And we can classify that impact in several different ways. We'll have a look at that in a little bit more detail later on in this module. Suffice to say, a SQL injection attack can leave a system in a real mess. So with that context set, let's move on and start taking a look at how an attack is actually mounted, the actual mechanics of attack. So let's go and check that out right now. I want to start with a real high-level view of what it means to mount a SQL injection attack. And we'll go into a lot of detail throughout the remainder of this course in terms of how to actually execute this attack. But let's start high level, and we're going to imagine that we have an attacker. Now this attacker wants to exploit a SQL injection risk. So they make a request, an HTTP request, a very carefully crafted HTTP request. And of course that request goes to a web server. Now that web server receives the request to the web page, and the web server constructs a query out of that request. So think about the typical things that a web application might want to query an underlying database on. This is the query that's being constructed in the injection attack. Now very often there will be a firewall sitting somewhere between that web application and the database. But in a SQL injection attack, it is still the web application talking to the database. It's not like the attack is going direct to the database. And this is one of the things that makes the attacks so successful, because it's still just website and database talking. So the query goes through the firewall and then all the way down to the database. The query executes in the database, and the database returns some data. Back out through the firewall, back to the website, and eventually back to the user. This request and response lifecycle is very, very typical, and it's exactly what happens when someone's just browsing around on the website. But in this case, the request is very carefully crafted to be malicious, to execute an attack within the database, so it becomes a very specially crafted query, and then return data which the application didn't intend to be returned back out via the HTML response to the attacker. Now here's where it gets kind of interesting with an injection attack. When the web application talks to the database, it must authenticate. So the web application has database credentials stored in it that it uses to identify itself when it goes to the database. And much of the discussion around SQL injection is, what is that web application actually allowed to do? What data can it read or write? What commands can it execute on the database server? And the thing is, that website is almost always going to connect to the database using the same identity, regardless of who the actual user is. It doesn't matter whether they're Bob or Jane, anonymous or authenticated. The web application almost always connects under the same identity to the database. And certainly many SQL injection risks occur because the credentials that that web application is using have access to do malicious things on the database. It's excessive access rights, but it happens all the time. And we're going to look at what can happen when those access rights are excessive, and later on in the course we'll also have a look at what you should do to constrain those access rights. Now, one other thing while we're on this slide, you can have different types of web application, different technology stacks. They could be ASP.NET, PHP, Java, different databases. So for example, SQL Server or MySQL or even Oracle. You have lots of different technologies that can make up this very generic picture that we see here. And the way the attack is mounted against those different technologies is different. So for example, there are language semantics between a database server like SQL Server and MySQL, which mean your query needs to be different. So if you're trying to mount a SQL injection attack against the database, you need to know how to query it. And it's going to change depending on the site and the technology stack they've chosen. So whilst we talk about this very generically here, the actual execution of the attack is going to change site by site. Now, fortunately, you'll also find that newer versions of technology are getting better at defending against these SQL injection attacks. So for example, we're going to look at an ASP.NET application during this course. And if you were to build an ASP.NET website today, you'd use technologies that implicitly make injection attacks very hard. You can certainly still find injection risks in these applications, but it is much more about falling into the pit of success from the perspective of the application owner. It's the old stuff that tends to have so many vulnerabilities. So go back to things like classic ASP. So whenever you see a .asp extension in the URL, that's the sort of stuff where injection attacks are rampant. So there are a number of different factors that go into the prevalence of the attack and how the attack is actually executed. But before we go on and actually start practicing some attacks, I want to talk about the impact. So what does it really mean when a SQL injection attack is successful? Let's go and have a look at that now. To understand the significance of SQL injection, we need to talk about the impact. So what does it mean for an organization when it all goes wrong and an attacker successfully exploits the risk? I want to talk about three things. And the first one is confidentiality. A successful attack can gain access to all the internal information within a database. So think about the sensitive sort of things that you've got in many web applications. Personally identifiable information, for example. Email addresses, phone numbers. That's very sensitive data. You've often got credentials in the database. So usernames and passwords. The impact of compromising confidentiality on that data class goes well beyond the system alone. because people reuse their passwords. So before you know it, a successful SQL injection attack against one application leads to the compromise of accounts in other applications. And of course, often that's because the password storage mechanism was insufficient as well. So that's confidentiality, leaking that internal data. The other issue is integrity, because once a SQL injection vulnerability is found, an attacker almost always has the ability to change data on the target system. So for example, they might change prices in an e-commerce site. They might add accounts to escalate their own privileges. They may inject malicious script, cross-site scripting for example, or script that mounts a drive-by attack in the browser by tricking the user into downloading and executing malware. Or in some cases, integrity could be impacted simply by the attacker deleting all the tables, just simply destroying the system. This is the risk of SQL injection. It can be extremely destructive. So these two together are pretty nasty, because for confidentiality, you could have someone in there siphoning off your data and not know about it, or integrity-wise, you could have someone destroying your data. Both of them are pretty unfavorable results. The third one is around availability. And when we talk about availability, a SQL injection attack can be used to simply take the service offline. So I just mentioned deleting data. That'd be one option. Dropping tables. Even severely compromising the operating system that the database runs on. Depending on the level of rights that the web application has to the database, the attacker can be extremely malicious beyond just the scope of the database itself. So if the risk is bad enough, that could be the entire system gone, not just offline, but completely destroyed. So that's confidentiality, integrity, and availability. Three attributes that we often talk about when we're assessing the security of a system. And all of them can suffer very, very badly from a successful SQL injection attack. Now, just to give you some context of how prevalent this sort of attack still is, let's go and take a look at a few cases of where it's still happening out in the wild. SQL injection in the wild. Now, a lot of people often say, is this still really a thing? Is injection still happening? Haven't we known about this for a very long time now? Surely we've got it right. But as we saw in that OWASP Top 10 document, it is still extremely prevalent. And it's still making headlines at an alarming rate. So for example, recently Drupal had a very, very serious SQL injection vulnerability. And in fact, after patching it, the guidance was, if you had not patched your Drupal systems within 7 hours of the vulnerability being disclosed, consider your system compromised. 7 hours! It's not even enough time for a good night's sleep. And that is in an extremely prevalent, very, very popular product. Another one we keep seeing SQL injection risks in is WordPress, and in particular in WordPress plugins. And unfortunately, they do tend to feature quite a bit when it comes to security vulnerabilities. SQL injection risks are found in these plugins all too often. And as we know by now, the ramifications of an injection risk in an application, even if it's in a third-party plugin, can be dire. So serious problems in both of those frameworks. And beyond that, there are just many, many, many cases of all sorts of websites built on all sorts of technologies which are exploited by injection risks. And the numbers are often huge. Hundreds of thousands or even millions of accounts exfiltrated by a successful injection risk. And it can be just as simple as someone having found the risk by a Google search and then using an automated tool to simply suck all the data out. So hopefully this gives you a sense of how real world and still relevant this risk is. It unfortunately is not a remnant of a bygone era. It's out there today, it's in a huge number of websites, and it's being actively exploited. Let's summarize the module. And I hope the first thing that is really clear is that this is a very serious risk. It's easy to find, it's common, it's easy to exploit, and the impact is severe. SQL injection must be taken seriously. And as we also saw, the impact on confidentiality, integrity, and availability can be catastrophic. And finally, unfortunately, SQL injection is still everywhere. It is enormously prevalent. And there are non-stop headlines about which system has been compromised by this really well-known attack. And this is the thing, it's been around for so long. It's very well known by builders and breakers alike. We know about this risk, but we still have so many applications that are vulnerable to injection attacks. So now that we've established just how big a risk SQL injection really is, let's move on to the next module and start taking a closer look at SQL queries. Because ultimately, if you want to exploit a SQL injection risk, you're going to need to understand SQL. In this module, I want to start taking a look at the fundamentals of SQL queries. Because if you're going to learn how to exploit SQL injection risks, you need to start developing a really strong capability around SQL as a query language. We're going to have a look at some of the basics in this module, and then as the course progresses, we'll get into more and more complex queries and commands within SQL Server. Now, as I said in the introduction, a SQL injection attack can be mounted against all sorts of different relational database management systems. I'm going to focus on Microsoft SQL Server, but I'm also going to point out where you need to be conscious of differences in the language semantics between SQL Server and other relational database management systems. So with that said, let's go and take a look at the overview of this module. So we're going to cover a number of different things in this module. And firstly, as I've said a couple of times now, the success of a SQL injection attack is really going to depend on understanding SQL. In the introduction of this module, I mentioned that SQL injection attacks are often automated. And certainly in those cases, you can just point a tool at a web server and let it go and do the work for you. But this course is about actually understanding SQL injection, knowing what's going on under the covers of these tools, and being able to mount an attack manually yourself. There's only so far you can go with automated tools, and particularly if you want to exploit the more advanced concepts within SQL injection, you're going to need to have a pretty good understanding of that SQL syntax. So at least a very fundamental knowledge of SQL is going to be very important. I'm also going to talk about basic database behaviors. So how does a SQL server actually behave? What can you do with a SQL server, at least beyond just creating and querying tables? And one thing you'll see as the course progresses is that you can actually get right down to the operating system level with the SQL injection attack. You can start running commands on the host if the web application and database server are insecure enough that they allow the attacker to do just about anything. And unfortunately, that is often the case as well. So that's all I want to talk about in the overview. And what I want to do now is go and jump into SQL Server Management Studio and start looking at some SQL syntax. Let's jump over there now. So here we are in Microsoft SQL Server Management Studio, and you may sometimes hear me refer to this as SSMS. Now we're going to be spending a lot of time in this environment because this is what's going to allow us to run queries directly against the database. Now this is not how you're actually going to mount an attack. You'll mount the attacks via the web application. But by sitting here in SSMS, it's very easy to show you SQL syntax, execute it, and then show you the results. So actually working in a query environment like this, or an equivalent for a different relational database system, is a really good idea when you're trying to craft your attacks, because it gives you somewhere to get your syntax right, validate it, explore the possibilities, and then move over to the target system and transfer those attacks into the web application you're attempting to exploit. So let's do this. I'm going to go and take a new query. Now I'm running SQL Server locally, so I've got the database engine running on my PC. I'm just going to connect to that, and I've got a sample database I want to use. So I'm going to just say use sample database, and we'll just execute that query. We now see just to the left of execute that we are now in the sample database. You'll notice a difference in case. Most of the time, Microsoft's SQL Server is not case sensitive. It'll depend on the collation in the database, but by default, most implementations won't check for a matching case. That's not always going to be the same with other database systems though, so do keep that in mind. So now that we're in here, one of the most common things you're ever going to do in a database system is simply select data. So, for example, let's just select everything from color. And clearly a star is a wildcard for everything. Now I can just press F5 to run this directly. And here we can see in our results panel, we've got 8 colors. Pretty straightforward. Now again, keep in mind that I'm going through this now because we're going to use some of these patterns in actual SQL injection attacks. Now one of the things we'll often want to do is rather than select every column, let's just select the name column. And we'll run that, and now we only have one column. Pretty straightforward stuff. What I want to do now though is filter this result. And in fact, I only want to get colors that have an ID of 4. So we'll run that, and of course we only get one color. Now differences in things like spacing, for example, don't matter either. So I could have a space between these. Run it again, runs just fine. So throughout this course, you may see different usages of spacing. The other thing we can do here is change operators. Doesn't have to be equal to 4. We may actually make this greater than 4. And of course, if we do this, we're going to get more results. Again, simple stuff. Now, one thing that we're going to see throughout this course, as we start exfiltrating data via an injection risk, is we're going to use an order by clause a bit. So let's take a look at that now. That's pretty self-explanatory. We'll run it, and here are our results ordered very nicely in an alphabetical fashion. Now we've got 4 results, starting with brown. Sometimes, particularly as we get into injection attacks, we only want to take the first result. So let's just take the top one. And now we only have brown. So this is a very basic select syntax. Let's now do this. Let's grab a new query, and what I want to do first is just check what colors we've got in that database again. And we'll run that. Okay, that's what we saw a moment ago. Let's go and do an update now. And let's say change purple to violet. So I'm just going to take a new command, a couple of lines down, and go with update color, set name equals violet, where name equals purple. Now because I've got 2 queries here, I'm just going to select this second one, F5 to run, and it will only run that one. 1 row affected. Let's go back to that select statement. We'll highlight it, and we'll run that, and now we have violet in row 7. But of course it's violet with a lowercase v. And as you'll see, the update still happened, even though I typed purple with a lowercase p. So I had purple with a capital P in the database, but because Microsoft SQL Server is usually case insensitive and the collation of this particular column inherits that case insensitivity, I didn't need a capital P. So as we go through this course and we're running commands, you'll see that I'll usually just do everything in lowercase. Doesn't matter if it's uppercase in the underlying database. At least it very, very rarely matters. So the last thing we might do here is let's do an insert statement. So I'm just going to jump down to the end, new statement, and let's insert into color in the name column a value of orange. Highlight it, run it, jump back up, run the select statement just to check, and now we can see orange is record number 9, which also happens to be color ID number 9. So all of this is pretty fundamental SQL syntax. Selecting from a table with a where clause, taking individual columns, taking only the first one, and of course it could be the first 2 or 3 or however many you want to take, and then basic update and insert statements. All of these are simple queries in the database. And where this is going to get interesting in terms of SQL injection is when we start mixing up the data and our queries from the application. Let's move on now and take a look at a couple of other common patterns in SQL syntax that we're going to use when we actually exploit injection risks. And the next one I want to look at is statement termination. Earlier on, we built this query, just a really simple select query, in order to demonstrate some pretty typical SQL syntax. Now, there's one thing that I didn't do with this statement, and I didn't terminate it. So SQL statements can be terminated with the semicolon. If I then run this query again, I get the same result. It's now terminated properly. I could then add another query. So for example, let's select star from the city table and run, and now we've got 2 result sets. So the semicolon allows us to terminate one query and execute another. Now, if we're just writing SQL syntax directly in somewhere like SSMS, we actually don't even need that. I can take this guy out, leave a space, and run again, and I get the same results. And SQL Server knows where one query ends and the other one starts. But the way we're going to use this semicolon syntax in a SQL injection attack is to chop a statement in half. So as soon as we put that semicolon, anything that comes after it is going to be considered a whole new statement, and it's not going to impact the original statement. So for example, if I take this out, I jump back up to the top line and drop in a semicolon here, the where clause won't execute, and we can see it's just got a little squiggly red line, because now as far as SSMS is concerned, this where clause is actually an entire statement. An invalid statement because you can't start a statement with where, but it's broken it in 2 parts because we've terminated the select statement. Now, if we were to actually run this, we'd get an exception. And I want to show these exceptions a little bit later on in this module. But for now, we've actually got a broken query. We could run this, and the first part would run, but the second part would fail. We'd have an exception. So what would I do if I wanted to ignore that where clause? And for that matter, the order by clause on the line after it? Well, for that, we're going to need SQL comment syntax. So let's go and take a look at how that works. We just terminated this first statement, the statement on line 1, by using a semicolon. So now everything that comes after that is treated as a new query. And of course, you can't just begin a query with where, so we've got some syntax highlighting saying that line 2 has a problem. But we can actually comment this out. So let's do this. Dash dash, everything goes green. Now order is considered the next query. Let's go and comment that as well. And now we've actually got a valid query. So I can run this again. And of course I'm just getting one result. So the point is here, I've actually combined 2 things. I've terminated the statement with a semicolon, and I've commented out both line 2 and line 3. So they're ignored. Now when we build SQL injection attacks, we're going to use statement termination and comment syntax in order to prematurely end queries and ignore anything that comes after our malicious payload that we're going to pass in via the app. The final thing I'll show you here is that we can use the dash dash syntax to comment one line, but we can also use the /* syntax to comment multiple lines. It looks like this. And I'll delete this one and close off the multi-line comment. And we can still run this and it works just fine. So 2 ways of implementing comments. And in fact, all of this could also be on one line. Doesn't matter, it's commented out. Everything between that /* open and / close syntax gets ignored by the parser. So again, as we start mounting attacks, we're going to use this syntax to ignore parts of the SQL query that we don't want going to the database. And in fact, we're going to use it to start ignoring parts of the original query the web application was making, such that we can inject our own malicious query and get data out of the system. So that's some query basics. Let's move on and start talking about the delineation between queries and data. In the next module, we're going to move on to actually exploiting a SQL injection risk. And when we start doing that, we're going to be working in the browser. And specifically, we're going to be working with manipulating the URL. Now, I want to give you an example of a URL and then talk about how this translates into a query. So here's a really simple example. mysite.com. Doesn't matter which site, but you can see here that there is a path called color, and it's passing a query string parameter called color ID with a value of 4. Now, SQL injection is all about manipulating the parameters in the web application such that it can actually change the underlying query. Now let's take this URL. Inevitably, this is going to get us the color with the color ID of 4. So let's switch back over to SSMS and have a look at what that query probably looks like. We could make a pretty fair speculation that when that URL we just saw is hit, it generates a query that does something like this. That's a pretty safe bet. It's going to take that number 4 from the URL and add it to a query like this. Now here's the crux of it, and this is really the crux of the entire SQL injection risk. This number 4 is untrusted data. So what I mean by that is that it comes via an externality. It's in the URL. It could be changed. And inevitably, if we change this from 4 to say 5, you'd get another color. This is simply the way web applications work. It's very fundamental stuff. But what we're going to start probing away at in this course is what happens when instead of 4 or 5, we start adding more query syntax here. Because you see, the 4 is data. Everything to the left of the 4 is query. Query, data. Query, data. There are 2 really distinct components that we're looking at on the screen here. And this piece of data comes from that untrusted source where it can be changed. So in this case, it comes via the URL. But let's go back and have a look at this query that we created just a bit earlier. This one where we actually changed the color. It's the same sort of thing here. We have 2 data attributes, the original color and the renamed color. And everything else here is the actual query syntax itself. So everything from the update statement here, all the way through to the where clause that checks the value of the name. And in fact, even that last single quote would be part of the query. The data is violet and purple. So let me jump back and show you a slide of what the web application's probably doing with this. Inevitably, that query we just saw looks just like this. So this is probably a post request to good old mysite.com, and we're changing the color. We're telling it what the old color was via the request body. So in other words, probably a form variable that's been posted with the request. And then of course, we're telling it what the new color is. Purple and violet, untrusted data because they're posted by the browser. I could change these. If this feature is designed for a user to be able to send the old color and the new color to the website, then there's nothing to stop them from changing purple and violet to whatever they want. Well, actually, that depends. If there is nothing to stop them, then they might be able to exploit a SQL injection risk. And indeed, in this course, we're going to talk about the things that should stop someone if they're not passing legitimate data. So that's a bit of an overview of how actions in the browser translate to queries in the database server. I want to move on and have a look at one more thing before we wrap up this module, and that's internal exceptions in the database server. So here's our query we ran earlier. Select top one name from color. But what if I did this? What if I, as an Australian, spelt color the way I normally spell color? Let's run this. Invalid object name, color. And in fact, we can see that color now has syntax highlighting that clearly indicates something is wrong, as does the column called name. And SSMS is obviously telling us that there is no table called color, and consequently it doesn't know what this column is called name. But the really important bit here, and this is what we're going to start really relying on for our SQL injection attacks, is the error message, that invalid object name, because that's actually telling us something about the database. If we could get our web application to run a query like this and return that exception, we, as external users with our attacker hat on, would know that there is no table in the database the web application is connecting to called color. Now that might not sound like a particularly useful piece of information, but this is the gateway to extracting all of the data out of the system. The fact that the system is actually leaking an internal implementation. And as you'll see throughout the remainder of this course, if we ask the database the right questions, by virtue of the untrusted data we submit to the web application, we will get answers that allow us to do very malicious things by exploiting the risk of SQL injection. Let's summarize the module, and there are obviously a few different things that we covered. Starting out with fundamental SQL syntax. But one thing that we also learnt pretty quickly is that it only takes one or two characters and you can fundamentally change the nature of the query. That semicolon, for example, that ended the statement dead in its tracks. As soon as the semicolon appears, that's it, the statement is over. Anything after that is considered a new statement. And then we looked at the commenting syntax in order to stop anything that followed the semicolon from actually being executed. Another thing I talked about quite a bit was this concept of query versus data. So in other words, what is the statement that's going to be consistent across all sorts of usage patterns of the website? So for example, select star from color versus the data, which is going to come from the website as untrusted data. So that is data that external parties could manipulate. So in that color statement, we had a where clause that was looking for color number 4. So 4 was the untrusted data, and we have to think of that very differently to the query itself. You'll see exactly why in the next module. And finally, we looked at error messages. And those error messages can tell us invaluable information about the internal implementation of the database server. So they tell us when a table doesn't exist, when we get a column wrong, when we try to run a query which is syntactically incorrect. The database server loves to tell us when we get stuff wrong, and it would be extremely hard for software developers to do their job if the database didn't do that. But we, as attackers, are going to exploit that talkative nature of the database and take these error messages to execute a SQL injection attack and start getting data out of the system. So let's move on now and actually start mounting SQL injection attacks. Now that we've got a bit of an understanding of SQL syntax, it's time to move on and start looking at the mechanics of a SQL injection attack. So we're actually going to start to mount this attack against a vulnerable website. So in this module, you're really going to start to understand just how to exploit this risk. Let's move on and take a look at what we're going to cover in this module. One of the first things I want to look at in this module is the 3 different types of SQL injection. There are actually a number of really fundamentally different approaches that you can take to exploit an injection risk. And it all comes down to what the application is actually vulnerable to. There are some very easy ways of exploiting SQL injection, but oftentimes you'll find the application has got sufficient defenses that you need to use a more advanced technique. So I'm going to talk about what those types are in the next clip. I also want to talk about how we can test for this risk and then also demonstrate how to show that an underlying risk does actually exist. And in fact, we're going to do that with just a single character. Get the right one, and that's all it takes to show that there's an underlying risk in the database. Now, speaking of underlying risks, I also want to show you what the risky code looks like. So what is it in this application that is making SQL injection possible? Clearly something has gone wrong at development time. What does that look like? I'll show you that in this module. And then I'll also talk about what input sanitization is, because that is one of the really important things that's missing when a SQL injection risk is possible. So we're going to talk about not only what input sanitization is, but we're going to look at a whole bunch of different characters that you are going to want to test for when you're looking for potential SQL injection vulnerabilities in an application. So we've got a whole lot to cover in this module. It's really going to start getting into the detail of injection attacks. So let's move on and start looking at those 3 different types of injection. When we talk about SQL injection, the attack normally breaks down into one of 3 different types of injection. And the first type, and one of the most common and easy to exploit, is error-based injection. So this is when the application is going to return errors raised by the underlying database server that we can then use to exploit the risk of SQL injection. Now, this is a very basic attack because the database is actually telling us things about what is in the database. And that could be anything from table and column structures through to what the actual data is. An error-based injection attack can be enormously simple, and that's going to be the first actual attack we see in this course. In fact, we'll see it in the next clip. The next type of SQL injection I want to talk about is union-based injection. And what we're going to do with the union-based SQL injection attack is take a result set that's returned by one query that the application's actually meant to execute, and then we're going to append our own query to that existing one. So we'll actually end up with 2 different result sets from 2 different queries. One is legitimate, one is malicious, but they're all going to be returned to the application, and then all of that data is going to be pumped back out to the website. It's a great way of exfiltrating data from the underlying database because it's just so easy to get it all out. It's just all pumped out in that result set. So that's union-based injection, and we'll start to execute that in the next module. Now, the third type of injection is blind SQL injection, and this is what we would consider to be an advanced SQL injection attack. And it's advanced because we have to fall back to this mechanism when neither error-based injection or union-based injection will work. We can't rely on errors from the system. We can't just pump exfiltrated data out appended to legitimate data, so the union-based injection won't work. We actually have to get a lot more creative. And it's called blind because we're not going to be able to directly see the data, not like with either of the other 2 attacks. So in fact, what we're going to do with blind injection is ask the database questions. And we're going to rely on the answers that come back implicitly from the database to make assumptions about the underlying structure and data. Now, there are 2 different types of blind injection that we're going to look at. One of them is called Boolean-based blind injection, and this is going to be exploited by effectively just asking this yes or no question. So if it's yes, then do this. If it's no, then do that. And then depending on what the database does, we're going to be implicitly told about what's going on inside it. So that's Boolean-based blind injection. Now there's also time-based blind injection. And what we're going to do in this attack is we're going to ask the database to just take a little bit longer to respond if a certain condition is true. So this is a classic timing attack. And certainly in security, there are many different ways of doing timing attacks against different vulnerabilities. And it's the same with SQL injection. We're going to use this time-based blind injection to force the database to change the duration it takes to run the query. Now that might actually sound like something very minor, but it gives us answers. If we can tell it just to take an extra second based on certain conditions, and we can observe that change in timing, that is a very powerful thing. And we'll see how that works as we proceed through the course. So these are the three key types of SQL injection attack. And we're going to look at all of these throughout the remainder of the course. But where I want to start is with that error-based injection. So let's move on and see that single character test that we can use to establish if an error-based SQL injection risk exists. It's time to start looking at actually exploiting a SQL injection risk. And what I want to do is use this sample website I've got here to show you how to find this risk. Now this website is from another one of my Pluralsight courses, Hack Yourself First, How to Go on the Cyber Offense. Now this is a really great course for going through a whole range of different risks in web applications. And amongst that set of risks is the risk of SQL injection. So it's a very handy place to go and actually test this risk. Now this site is public. It's over at hackyourselffirst.troyhunt.com. So you can go there right now and test this risk of SQL injection. And we'll be using this site throughout the remainder of the course. So it's a great resource to go and experience this firsthand yourself without having to set up your own database server and web application. Now the idea of this site is that it's intended to represent a way for people to vote for their favorite supercar. So that's why you'll see things like a leaderboard. You can see a supercar here in the banner at the top of the page. And as you can see from the title in the top left corner, it's called Supercar Showdown. You can also register and log in and search and do a few other things that we won't use in this course. But again, if you do want to take a look at that Hack Yourself First course, all of that is used fairly extensively. And it also has a pretty extensive range of vulnerabilities in it. What I want to look at now though, is right down the bottom of the page. So let's scroll down and we'll see that there's a section here on cylinder layouts. And what we can see here is that we have a different number of vehicles for different cylinder configurations. So for example, we've got 3 V8s. Let's go and have a look at those guys. So here are 3 cars, every one with a V8 engine layout. Now what we'll notice in the URL is that V8 appears here in a parameter called cylinders. So this is just a query string. This is all it is. A query string saying, hey, get us the V8s. If we change V8s to V12s, we'll get a different result. It looks just like this. So here are our 4 V12s. Now this is a very common pattern in web applications. The query string parameter is simply describing the nature of the data that the page must show. There's nothing wrong with this. It's a very natural way of building applications. And what inevitably happens is that that query string parameter is somehow impacting the underlying query in the database. So you can imagine having a table somewhere in the database called supercar, and based on the name of this query string parameter, probably a column called cylinders, and then a query is being built up, and it includes a where clause which says, get me everything from the supercar table where the cylinders is equal to V12. So that's pretty basic stuff. Now let's make it a bit interesting. I'm going to change the URL, and I want to use just one single character to test for the risk of SQL injection. And that character is this. A single quote. That's all it is. Let's load that page up now. So here we have something a little bit interesting. And clearly this is an exception, an unhandled exception at that. So something has gone wrong in the application. And rather than the application just simply saying, hey, something has gone wrong, and having a nice friendly page, maybe the ability to submit an error report or something like that, instead, we've got this internal exception that has bubbled up into the browser. And the exception tells us a lot of things. So one of the things it tells us here, in this section on exception details, is that it's a system.data.SQL client.SQL exception. Now this application is an ASP.NET MVC application, a model view controller application. So a very typical pattern for building web apps on Microsoft Stack today. It's also sitting on top of a SQL Server database. So what we're seeing here is that this internal exception in ASP.NET is returning an exception raised by the database. So that's the bit here on SQL exception. So the database has actually told us that something has gone wrong. And in fact, what it's told us is that there is an unclosed quotation mark after the character string v12. And in fact, what you'll notice here is that v12 is encapsulated by single quotes. Well, kind of. There's one single quote before v12, but two single quotes after v12. Now in the next clip, we'll have a look at exactly why that is. So the other thing that this exception is actually telling us is that this is an error-based SQL injection risk. So I just talked about error-based risks alongside union and blind risks. This is what error-based looks like. It's the database very explicitly telling us something about the internal implementation of the system. And in this case, it's obviously telling us that it can't actually parse the query. We'll look at other really sensitive things that can be disclosed via error-based SQL injection as we progress through the course. But I just wanted to touch on one more thing first. This is an HTTP GET request. So we've made a request to this URL using the GET verb. That's what implicitly happens when you type a URL into the address bar, or when you change one in the address bar, as the case may be here. SQL injection risks are by no means constrained to GET requests. You could have a SQL injection risk in a POST request. So if we filled out a form, for example, we could well see exactly the same response if we had an extraneous quote in there like here, which wasn't properly handled. Many applications these days are also using semantic HTTP verbs, things like HTTP put and HTTP delete, because they have very specific meanings. And the point is that none of those verbs, get, post, put, delete, all of these commonly used HTTP verbs are equally at risk of SQL injection. So even though it's probably easiest just to go into the URL and mess around with query string parameters, this risk is by no means constrained to GET requests. With all this understood, let's now move on and actually start to modify the query structure such that we get this page to do something that it was never designed to do. So in the last clip, we managed to get this page of the Supercar Showdown application to raise this internal exception. So again, this is the error-based SQL injection we're looking at here. And we managed to get this error to occur simply by appending a single quote to the URL. It's now been URL encoded via Chrome, but that %27 is the URL encoding syntax for a single quote. And in fact, it's this extraneous single quote sitting at the end of the internal exception here, which is the one that we've entered. Now, all of this begs the question, what's actually going on underneath. So what has caused this exception to be raised? To understand this, I want to jump over and show you what the query string looks like and what that's translating down to in the underlying database query. Let's start to break this whole request and query thing down a bit and see what's going on. So here's the query string that we had originally. So this one is perfectly legitimate. So the resource is cars by cylinder, the query string name is cylinders, and the value is V12. Now I've put V12 in red because that's effectively our untrusted data. So that's the stuff that we're manipulating and that you must always expect an attacker to manipulate. Because they can do whatever they like with it. It's just part of the URL. And likewise, any data from things like the request body, if a form is posted, or even the request headers are all untrusted data. So any of these things can be manipulated by an attacker and changed to whatever they like. So here's what happens. Cylinders V12. This then gets translated into a query like this. Now this is pretty basic SQL syntax. It's just the same sort of stuff as we looked at in the previous module. The real key thing here is again the text in red. So this where clause, where we expect the cylinders to be V12. Now you'll notice that V12 here is encapsulated in quotes. It's a string, and that is a specific data type within SQL Server. In the URL, everything is a string. It may then be typecast to an integer or a date or something like that, but in this case, it's been passed through to the database as a string. So here's what we did next. We added a single quote to the URL, so just off the tail end of V12. What happened then was that caused this SQL statement to look like this. So see how we've now got two quotes off the end of V12. Now this is no longer valid SQL syntax. And in fact, as far as SQL Server is concerned, we've now got an unclosed quotation mark. So basically everything is unbalanced. And that's exactly the exception that we saw bubble up into the web interface. Unclosed quotation mark after the character string, and then it had V12 with one single quote on the left and two single quotes on the right. So this is what caused the exception. And just as we saw in the previous module, when there's a problem with your query, SQL Server tells you. It tells you exactly what is wrong. Now, of course, this is meant for the developer, for debugging purposes. It's not meant to go back out to the public, because not only is it a nasty experience, but it also allows us to start exploiting underlying risks using error-based injection. We're going to look at that in more detail later on. For now, the important thing is that we know that there is an underlying SQL injection risk. So let's start to probe away at this a little bit. What if we change that query string parameter from V12 with a single quote to this? Now this starts to get a bit interesting, and it's interesting because of the way it translates down into the underlying SQL statement. That would cause our statement to look like this. So there are a couple of key things that are going on here. So number one, that V12 string is being closed off with the single quote that we passed in the query string. The next thing is we've passed an OR operator. So now we're actually adding another condition to our where clause. Now after the OR operator, we've got this 1 equals 1 condition. And clearly 1 equals 1 is always going to be true. Now combined with the OR operator, it's effectively going to negate the V12 condition. It doesn't matter that we're looking for cylinders that are V12s, because after that we say, or if 1 equals 1, which again is always true, then return the result. So this actually fundamentally changes the nature of the query. It's no longer a filtering query. We're just going to get everything. So the final thing in this query worth noting is the double dash. And per the last module, we saw that this was the comment syntax for SQL Server. So that double dash in the query string filters down into the actual SQL query itself, and it cancels out that last single quote. So on that bottom line, everything in red is what's come in via the URL. So again, the untrusted data from the user. But what it actually means is that that last grey single quote never gets executed. It's commented out. And if it wasn't commented out, we'd have this problem of an unclosed quotation mark again. So exactly the error we saw in the error-based SQL injection just before. So this is the new query string value that I'd like to use for the cylinders parameter. Let's jump over to the browser and see what happens when we change that query string value to this. So here's what we'd run just before, and this was the one that raised the exception, because again, this %27 up here in the URL was just a single quote. So let me now enter the query string that we saw in the slide just a moment ago. So here's the whole thing. V12 single quote or 1 equals 1 and the double dash comment syntax. Let's see what happens now if we load this page. Okay, so this is interesting. We have actually now got every single vehicle in the system. We've got everything from the 16-cylinder Bugatti Veyron down the end, all the way back up to the 6-cylinder Nissan GTR. And we've got all of it because of the OR operator and the 1 equals 1 condition. It's always going to be true. It entirely negates this V12 requirement. Now there is actually a term for this. It's called a tautology. Let me show you what I mean by that. When we talk about a tautology, we're talking about a formula that's always going to be true. And that's what the OR 1 equals 1 does. So we can append that to a query and we can negate every other condition in the query because it always makes it true. Tautologies are a very powerful construct that are used extremely frequently in SQL injection attacks. And they can be used for everything from returning the number of results that you see on a page, all the way through to entirely circumventing password validation on a website login. And in fact, that is a really important one, and it frequently comes up as an example of just how malicious SQL injection can be. So let's move on and have a look at what that attack would look like. One where we get to log in as whoever we'd like. Let's go and check it out. Obviously, something like the ability to circumvent an access control is a pretty serious exploit. It's one of the most fundamental things attackers like to do. How do we get around the fact that this resource is only meant to be accessible to authorized users? That is often the very essence of hacking. So let's take an example of where we can use a tautology in SQL injection to log in as someone else. Now let's imagine this. You go to a website, you log in, and these are the credentials you provide. As in the previous clips, I've put the untrusted data in red. So imagine this time it's a form on a web page. It's going to be an HTTP post. There's one field called username, one called password. We're going to pass these values. Now inevitably, this particular login is going to translate down into a SQL statement that looks something like this. Now there are a few things that I want to point out with this SQL statement. So number one is it's clearly just looking for an occurrence of a user with a username of John Smith and a password of password with an @ instead of an A. The reason it's doing a select count star here is it's just trying to find how many of these exist. And of course it should really only ever be 0 or 1. And really this statement is just going to return an integer. If the web application gets back a 1, it says yes, this person does exist, their credentials are correct, let's log them in. The other thing I want to point out though is that this would be a very insecure password storage mechanism. And it's bad simply because there's no cryptography applied. This statement shows that the password is just stored in plain text. So certainly no good strong cryptographic hashes for password storage, which is what we really want to see in a database. I'm showing this query here though, because it is a very canonical representation of how serious a SQL injection risk can be. But again, if this is possible, the web application has got bigger problems than just SQL injection alone. Be that as it may, let's proceed because I wanted to talk about this tautology. So what if we add our OR operator and our 1 equals 1 condition up here in the username? Now again, I've kicked it off with a single quote to close off this username string, and then I've trailed it with the -- comment syntax. Now here's the problem if this gets translated down into the SQL query. It'll look like this. So let's look at what this actually does. After username equals John Smith, single quote, close off the string, here's our tautology, the OR operator, 1 equals 1 always being true, and then everything else commented out. Now think for a moment, what would be returned by this statement? So this is a count star. Forget about username equals John Smith. That's negated by OR 1 equals 1. So what you're actually going to get is a count of the entire number of records in the user's table. Now how successful this is after that will really depend on the way the application is handling the result from the SQL server. So for example, if the application is saying run this query and if the result doesn't equal 0 or if it's greater than 0, the user gets to log on as whatever username they provided. That would be a problem. This would be a serious SQL injection risk. On the other hand, if the application said, look at the result from this query, and if it equals 1, then allow the user to log in, now there's a problem. Because this isn't going to equal 1. It's going to be 100 or 100,000 or however many users are in the user's table. But as an attacker, we have a little trick, and it's this. So see what just happened here? I'll go back. Here is OR, 1 equals 1. Now it's AND, 1 equals 1. So this changes the nature of the query. And now, rather than negating username equals John Smith, it's requiring username equals John Smith. So it will only return one record. 1 will always equal 1, and the username will equal John Smith. So now we're only going to get one record, and if the application is only looking for one record, then the user will be logged in. But of course, this is actually pretty verbose. So what if we just did this? Just commented everything else out. Now it's actually very simple. The only where condition is that there needs to be a user called John Smith. Password doesn't matter. Any other tautologies off the end of it also don't matter. This becomes very, very simple. But of course, there is a caveat. And the main caveat is you've got to assume that the username is going to come before the password in the SQL query. Now it's very easy to describe how this might work when it's all pre-prepared and it's on a slide, but it's very different when you're remotely executing this attack and you've got to make assumptions about how the underlying query is written. So the OR 1 equals 1 clause can actually be much more useful when you don't know the order of the conditions in the where clause, because it wouldn't matter where that OR sat, it would always be true, the tautology would always work, and you'd always be logged in. The reason I wanted to show it to you this way is just to demonstrate how many semantics there can be in the execution of an attack like this. And you've really got to start to think about all the different possible ways the query might be put together based on that untrusted data from the web application. It requires a lot of trial and error, and particularly as we progress into more sophisticated attacks, a lot of background in terms of how the SQL query syntax actually runs. So this is one very good example of a malicious attack. Let's take a look at a bunch of other possibilities when you can mount an injection attack like this. There's a heap of stuff you can do once you have the ability to change the structure of the underlying query. So let's imagine the example from the previous slide, where we've got username, and we can put whatever we like in username. So what about one like this? Have a think about what is happening here. We're looking for a username of John Smith, and then we're closing the query. That semicolon, that's it, query ends. Everything after here is now a new query. And in this case, we've just changed everyone's password to foo. That is a really simple attack, but that is also very, very, very powerful. Now that's a pretty invasive attack to run. Try that and the owner of the website is going to discover that there's a problem probably pretty quickly, assuming people do actually say, hey, I can't log in anymore. Here's another example. What if we did this? So in this case, we're actually manipulating prices. And in fact, it's reducing the price of every item by 1. So assume it's, say, $1. Every single record in the item table just had the price column reduced. Now that sort of attack might be a little bit harder to pick up on, particularly if you started doing something like using a where condition to just reduce the price of one thing. Perhaps the attacker is just reducing the price of the one thing that they're about to buy. And if they can do this, they can put the price back up again afterwards and possibly cover their tracks. Another angle with all this is to use something like an insert statement. Doesn't matter what you're inserting into, the point here is that you can start to do some serious things in terms of modifying the underlying data. Perhaps we're inserting into the users table. Perhaps we're setting the new user that we insert into there as an admin. The possibilities with a statement like this are limited only to the nature of the underlying data. If you can run this and insert into any table, you can do some really serious damage. Now, of course, this is only going to work if the account that the web application is connecting to the database with has the rights to insert into the target table. And that is a really, really important concept in SQL injection. It's particularly important when you get to malicious statements like this. Dropping tables. Does the account that the web application is using have the rights to actually change the underlying schema? This is really nasty because now you can start to talk about malicious damage, availability damage. This has just dropped the entire users table. The system is now pretty well offline for anyone trying to access that table, but it only happens if that web application can actually drop tables, which it really should never be able to do. But we'll get onto that towards the end of the course when we start talking about the principle of least privilege. And a final one. What if we did this? So actually creating logins. So now we can start to talk about privilege escalation. Because if you can create a login to the database and assign it rights, you can now create a backdoor for the attacker to just get direct access to the database. Why go through the web application and have to do all this hard work on SQL injection if they can just go straight into the database? Now again, you need the rights for the web application to be able to execute this script, and you'd also need the rights for a remote user to be able to access the database directly. At least you'd need that to be able to make any use of the new login. So if the database was firewalled off from the public web, you couldn't ultimately do a whole lot with this. But certainly you can see the potential. So that's a few very malicious things that you can do with SQL injection. Let's now jump over and have a look at what this risk actually looks like in the code. So what's making all of this possible? Here's the code that's running in the background of this web application. Now, as I mentioned earlier, this is an ASP.NET MVC web application. So this is the controller that's called when there's a GET request made to this path, cars by cylinders. Now this path takes one parameter, and it's this one, the cylinders parameter. And what happens in the code is that this cylinders parameter is taken down a couple of lines below this, on line 15, and you can see it already highlighted in a string containing SQL syntax. So this query is just being manually built up, and the data concatenated with the query. So in the last module, I talked about the differences between query and data. We looked at this when we looked at updating colors, and we had purple and violet. That was the data, and the update statement was the query. And what's happening here is that once you get past line 15, they're all mixed up together. It's just concatenated. So the application, and certainly the database server, doesn't know where the query ends and where the untrusted user data begins. There's absolutely no validation that the cylinders parameter here actually contains valid cylinders, and the application is just blindly taking that parameter, throwing it into the statement, and executing it against the database server. Now later on in the course, we'll look at how to do this securely using SQL command parameters. And that's going to fix this problem right up. But one other thing that's missing here is input sanitization. So there is nothing here that talks about what is allowed in this cylinders string. And as we now know, we can pass a lot of stuff into this parameter which we really shouldn't be able to. So a really key thing with SQL injection is validating that untrusted user data. So really here we should be saying, before we do anything, does this data conform to a known good pattern? And what we really want developers doing is actually whitelisting those patterns. Now think about what should be passed through here in cylinders. We've seen an engine configuration and a number. So in the case of our application so far, you could almost just whitelist it. You could have V6s, V8s, V10s or V12s. Anything else shouldn't be allowed. You could be a little bit more generic and regex it. There must be a single letter followed by a 1 or a 2-digit number. That would cover everything we have in the system at present. You might even get a little bit trickier and say, well, what happens if we end up with a flat 6? We start adding Porsche 911s. Well, in that case, we might want to whitelist cylinders just to alphanumeric and spaces. So that would be a very constrained list of allowable characters. If you only allowed letters, numbers, and spaces, there is no way you could mount any of those attacks that we've looked at to date. Quotes would be disallowed, semicolons disallowed, equals sign disallowed. All of these attacks would fail. The trick for you now, as an ethical hacker, is to understand what sorts of characters might be useful to test against the application to see if there is any input sanitization happening. So let's move on and have a look at exactly how input sanitization works and what some of the characters are that you should be looking out for. Let's talk about how input sanitization should work in an application like this. So here's what's happening at present. We've got an attacker, and that attacker is going to send a request to the web server that looks like this. So this is what we saw just before, and clearly this is a SQL injection attack. As we now know, the web application is going to take this query string parameter and it's going to make it look like this particular statement. Now, because of this or 1 equals 1 tautology, the database is going to return every single record back to the web application, and the web application is going to spit it all back out to the attacker. Injection attack successful. But let's do this. Let's scroll all this back and we'll imagine that the website is now actually sanitizing the input. So it's going to look at this query string parameter, so the untrusted user data, and it's going to decide whether this is valid or not. Now this to me doesn't look valid. And we just talked about the reasons why. So in this case, it's not just a V and then an integer, or even just alphanumeric and spaces. It doesn't conform to a valid pattern for cylinders. So with input sanitization in place, it's going to do this. Rejected. That's all. It's that simple. And it's just a matter of the web application saying, hey, this is not a good request. It doesn't conform to one of those allowable patterns I just explained. So getting back to the sort of things that you want to be looking for as an ethical hacker, let's go and have a look at a whole bunch of different character ranges that you should think about for testing input sanitization. Here are some good examples of characters that are often used in SQL injection attacks. We've seen some of these already, so things like single quotes and dashes and equal signs. Many of these are used to mount an attack. There are also a whole bunch of others that we haven't looked at. Things like percentages that are often used in like clauses, the @@ syntax to access server variables. All of these are the kinds of things that you want to test for when you're establishing what sort of sanitization is going on in the app. Now you'll see I've also got regex patterns in here for A through to Z, both lowercase and uppercase, and for numbers. Now that's not to say you should never use letters because they could be involved in a SQL injection attack, but it's about establishing what is allowed by the app. Because in many cases, you are only expecting an integer, particularly when things like an ID is passed. The application shouldn't be allowing letters. That would not pass what should be a whitelist rule that says only give me numbers. So this is a really good character set to start using. Now sometimes you'll see that I've got double characters, so the @@ syntax for example. The web application may legitimately need to accept the @ symbol. Email addresses are a great example of that. But does it need to legitimately accept the @ symbol? Now I'm a little bit pragmatic here, and I want to be cautious about recommending that an application should be too overzealous in its whitelisting, because the last thing you want is to make the application unusable. There are many examples of problems like folks in Ireland not being able to register on a web application because of the prevalence of a single quote in the surname. That's the last thing you want. Well, other than a SQL injection attack, it's the last thing you want. But it is the sort of thing you want to test carefully to determine what sort of characters you might be able to use in an injection attack. Let's summarize the module. And the first thing we looked at was these 3 different types of injection. Error-based injection. And we saw that in this module, that internal SQL exception bubbling up through the web application, which wasn't keeping that error private. Union-based injection, combining multiple results together. We're going to see that in the next module. And blind injection, that advanced injection attack, where we'll look at Boolean-based blind injection and time-based blind injection later on in the course. The main thing is, though, 3 different approaches of varying degrees of complexity that may be required depending on the nature of the app. Now, we also saw how simple SQL injection can be, because it can just be one character. That quote is the canonical single character injection test. So many times, it just takes that one keystroke to demonstrate that there is an underlying risk which now deserves a little bit more probing. Now, one of the ways that you might do that probing is with a tautology. So this always true sort of function, where we append something like a 1 = 1 to a clause so that that is always true and it can actually negate another condition, such as looking for a particular record or filtering the result set down. So tautologies, very, very useful. And as we saw, they can even be used to circumvent access controls by exploiting the login. And finally, we looked at sanitization of this untrusted data. So the data that comes from an external party that could be malicious. Certainly as an ethical hacker, you're going to try and make it malicious to see if you can break through the defenses of the app. And you really want to understand how good that app is at actually recognizing that malicious data. So is it doing what our app just before was doing and just letting anything in, so being very, very permissive? Or is it saying that only certain strings are allowed? And if your payload as an attacker gets through sanitization, then you know the application might have some serious problems that deserve a bit more probing. So that's the fundamental mechanics of SQL injection. It's time to go on now and start looking at how we can find the underlying schema, and the really important part of this course, actually starting to extract data from the target application.